converter, and fundamentally controlling the speed around the synchronous speed of the double-fed induction generator system. The beauty of this one here is naturally the scale of the power converter is maybe only 30% of the total system, but on the same time having full control of it. The alternate solution is the full-scale converter, where we control the power fully of the generator, doing AC to DC, and then interface to the grid doing DC to AC. And this gives full controllability, we can say, and maybe also a wider variable speed range. What is also coming out of it is the ability to decouple the two systems. So if something happens at the grid, we can decouple it to the generator and also opposite. However, the challenge in general with this technology is we have to convert the power twice, while we don't have to do it up here. And it is a major challenge compared, but more and more large-scale turbines, they are going into this direction because of this feature and also cost reduction. And the features of the different generators being applied in terms of being able to handle voltage sags, also delivering reactive power, is illustrated here as well, as there is a discussion about, okay, what should the gear ratio be of the system? Do we need a gearbox, or do we want to have a direct drive? Here are some of the, let's say, benchmark of that. I think the general trend is, seen from a turbine perspective, is to have some kind of a gear ratio between the generator and the rotor, because as the rotor size increase, the speed, rotational speed becomes lower, and then the diameter of the generator becomes too high. So this is a general trend for the technology. In order to control systems like this, we can say that we fundamentally have maybe three levels of controls. Here you have the turbine, you have gearless, then you have the different generators, we have the grid over here, then we have the AC to DC and DC to AC converter. And that three levels of control, at least, one is really to control the current, very precise and safe, and as well as doing grid synchronization. This we do very fast. We really have to keep, let's say, the information level very, very high, and we have to react on demand, if we can say so. Then we have the wind system specific controls, maximum power point tracking, operating with power limitation, grid support, and so on. And then we have more advanced control features which come along the development of the grid, and that is maybe voltage regulation, frequency regulation, improve the power quality, as well as being able, for example, to do black start if that is needed in the power system. And of course, I would say this part here is constantly developing in order to make the technology better. The converter topologies we are applying are divided into two categories, I would say. It's below 690 volts. That gives, let's say, a low voltage scenario in terms of implementation. And of course, in the power electronics area, we know this is a two-level voltage source converter which is applied. If the generator has synchronous generator characteristics, that means the voltage is generated by the generator itself, then we do not need to have an active converter to control the frequency and so on. There we can just apply a boost converter, and then we have a DC to AC converter to the grid side. So this is really used a lot, and this is also used in a lot of other industries. And if we want to scale up the power, we cannot just do it with one converter, so we have to do multiple of them, power stacks, as we say. And in such case, maybe this we have bricks of 2 megawatts. So if we want to do a 10 megawatt system, then we have 5 of those units, and then of course we can optimize the operation. And in that case, we will also have a redundancy if one of them is failing, if we do it properly. However, if we really want to have high reliability, because then here the generator is one big one, we could imagine that there are more windings in the generator, and then have a multi-winding generator, for example, 9 phases or something like that. And then we have a converter per phase set, if we can say so. For example, 2 megawatt, and then 3 of them, this is a 6 megawatt. And in that way, we get a way even higher reliability, availability of the system if there are failures, for example, in the winding of the generator. When the power goes up, it's a natural thing to think about going beyond 690 volts and then go into the medium voltage domain. And in that context, apply, for example, a 3-level converter. Then the DC link voltage here becomes higher, and we will also have a medium voltage generator. There are many arguments for doing it in terms of efficiency and so on, but the challenge is a little bit that then the protection schemes in the wind turbine becomes different, and it's more difficult to handle in practice and also in maintenance. But this is constantly going on, and we see more and more wind turbines also moving into the medium voltage domain. But of course, if we look at it, this was the first technology I was discussing, low voltage. Then we have the medium voltage. In both cases, we have a transformer to transform up the voltage. And in that way, then have the collection grid, for example, in a wind farm. It's a natural thing to ask the question, okay, could we maybe avoid this 50 hertz transformer or 60 hertz and then go directly into the collection grid without that, because then we can save a lot. And doing, let's say, a medium voltage, high voltage wind turbine generation system, and then we have the voltage level of 12 to 66 kilovolt. Technically, yes, it's possible. Cost-wise, it's more challenging, and it's also more risky for the wind turbine manufacturers. So this is still a pending, let's say, things. There are features which are illustrated here, but the challenges are insulation system, short circuit protection, and of course safety in the system. We move things into collected plants, if we can say so, and there we can transmit the power AC-wise or DC-wise, right? And this is dependent on the length from, for example, offshore to shore. And if it is AC, of course, it's like this, maybe 66 kilovolt AC grid, and then high voltage AC cables. If the distance is long, then we have HVDC. And what, of course, we could imagine was a solution where we do not do DC to AC and AC to DC, but just do AC to DC and then DC to DC. So in that way, we are maybe saving conversion states and having a medium voltage DC grid. Still, we have not seen this, but maybe we can learn from the photovoltaics in terms of how to do this. If the distance is long and we are using AC systems to connect to the shore, then we have to compensate for the reactive power in the cable. And in that context, there is also an evolution in terms of the power electronics by doing what we call a STATCOM, which is able to deliver reactive power, as well as able also to help with other critical situations, for example, low voltage right through, and also compensate, for example, for the harmonics. And this is coming more and more, that the power electronics is also put into place in order to compensate for the reactive power in the cable system. Okay, time is running. Let me just briefly discuss energy islands, because this is an aggregation of a huge amount of wind turbines, and what do we do there in terms of electrical infrastructure. So now I take the case of, let's say, around Europe, because it's really also involving some of the neighboring countries, maybe even more because we are a small country. But there is in Europe a plan of putting a lot of wind power into the ocean, and really, explore 35, maybe even more gigawatts of wind power offshore to power Europe, if we can say so. And in that context, let's say there are plans and tenders on the way for making, let's say, power plants in the gigawatt size, and then collect the power and distribute the power out to the countries, or doing something else. And here the concept of energy islands has been proposed. For example, in the ocean, 100 kilometers, 200 kilometers away from shore, uh, have a lot of wind farms, 1 gigawatt each, maybe 10 gigawatts here. Uh, have a artificial island, or an island where we collect all the power, and then for example, transmit the power by DC lines to different countries, or as there is also a high demand of doing electrical based, as e-fuels or e-gas and so on, do hydrogen at least, and place also, let's say, hydrogen electrolyzers on those islands, and then maybe transport the hydrogen by pipes instead of doing electrical transportation. There are pros and cons by doing this, and there are also expenses, of course, in making an island. But the first place where such kind of thoughts have been has been also under discussion. It is being implemented now, and that is the let's say that is on Bornholm, where Energy Islands is being built fundamentally, where we have a certain capacity, and then we can connect through HVDC lines to Denmark and Germany. And here is, let's say, the fundamental architecture, where 1 gigawatt is, let's say, installed like this, and then we have an HVDC connection which can goes to Denmark. You can see here the voltage level, and then we have another 2 gigawatt facility where also connection is, and it can go to Germany, and then it's possible to go, let's say, connect them both so they can deliver to the different countries. So it's a 3 gigawatt of installed capacity. But of course, and this is relatively regulatory way to do it, and the standards are available. But of course, doing such kind of things and is of course important to say, okay, how can we ensure a stable and resilient hub, if we can say so, but also what is the economic most feasible way of doing such kind of system implementation. And in terms of AC grids, if we are doing such kind of system on an island, then the question is, of course, okay, today we have grid codes which are very relatively demanding for the technology. Could we, in case that we have an isolated system, could we release a little bit the grid code so we could do savings in the wind turbine technology, and at the same time have the same level of reliability and availability? So that are some of the things which are really being discussed a lot, especially in terms of this wind farm located more in the North Sea of Denmark. And then, of course, also whether the system should be, let's say, an AC hub based. Here you have, for example, 4 megawatt of capacity. We do AC power connection, and then we do AC to DC, and then transmit the power. Or should we go directly into a DC hub when we produce the power, and then connect it to the system? There are a lot of cost considerations and also performance considerations when doing such kind of system. Okay, it's coming to an end, but some of the other trends related to the wind power technology, not all of them are related to the power electronics, but there's no doubt that the foundations, so the water deep of the oceans are important in terms of the cost. So floating wind turbines are a lot under discussion. How can this be done, and also how can it be controlled? And at the same time, let's say, have a good cost of energy. Integration of storage in the system are under last discussion, either at the wind turbine or a centralized storage capacity. HVDC technology is, of course, as I illustrated before. When we are going up in power, which converter topologies are the most feasible, and having in mind, of course, also, let's say, the reliability of the system. Here, a natural question is also, when will the wide bandgap devices come into play, because the wide bandgap devices will typically have a higher efficiency or can reduce, let's say, the size because of the switching. Control technology is under last discussion. Should the turbines operate in grid following mode, just provide active and reactive power into the grid and assume the frequency is available, or should the wind turbines also contribute to the formation of the grid, and thereby control the grid side converter of the turbines in a grid forming mode? And how can this be done in a proper way, combined with that we are dealing with a very complicated mechanical structure in the system? And then grid codes in that context will, of course, dictate what to do or advise what to do. And we will also see a continuous, let's say, growth development of that part, just to mention some of the important aspects. But there's no doubt that the power electronics is playing a key role for doing part of this. And then last, I would just say, very recently, we did a paper where you can download power electronics in wind generation systems, and so you are welcome to download that and get very recent references also, which are available. So as you can see, I have not maybe taken Denmark as a case that wind is really an important contributor to the electricity generation. And we are constantly developing the installation, and we have a strong trend to the offshore. Onshore, it's very difficult to get wind turbines erected, because you can see we already have around 5,000 wind turbines raised. So while offshore there is a bigger capacity, but at the expense of higher cost. And what I also hope you got of impression by this presentation here is that this cannot be done without the power electronics technology. It gives all the features. However, we should, of course, also respect all the mechanical material developments, which are, of course, also very, very important in order to be successful with the technology. With that, thank you very much for your attention, and I think there are also time for a few questions.
Yes, colleague Blabjak, thank you for your very interesting presentation. Is there some question from the auditorium around here? Otherwise, I want to ask a question. There was, I cannot remember the number of the, there was some slide in the middle.
Yeah.
You mentioned there fixed speed wind turbines. So
yeah.
I'm not so deep in the wind turbines. Means it is just a motor connected to the grid, or maybe some pole switch when the motor has two pole pairs or something like this. Is it this? Was it this?
It was this. Yes, or correctly in the old times when the technology and that. Okay, maybe I can share again. So because nobody can remember. I think it's this one you challenged me a little bit about, but I can also go back to, let me see.
No, it was
This
a
one.
slide.
This
Yeah,
one.
this one. This
Yeah,
one.
yeah.
Yes,
Yeah,
yes,
yeah. Yes. It's totally right. Well, very good scene. As before 2000, the wind turbines was typically an induction generator, and then it was connected to the grid, and then it
Exactly.
run with almost fixed speed. As you know, the slip is of course the difference dependent on the wind production, and then dependent on the let's say how the wind was, then you saw immediately what that's going on into the grid. And of course, you can imagine that if you have a fixed speed and you have wind gust and so on, you will see that in the structure.
You
And
cannot control.
yes, and no
Yeah.
control of the power. So
Mm.
the first 20 years, all the turbines installed, they were small at that time compared with the big generators. Was this technology? But of course, when things become more dominant, this was not.
Yes, of course. I couldn't
Yeah.
believe this.
No, but that's really
We
true.
we have around here, we have also some wind turbines, maybe smaller, older, and they
Yeah.
told me there is a pole pair
Yeah.
with a relay, and I couldn't believe this so much.
Yeah, and that's right. So this fixed speed is maybe typically two fixed speeds. As it's totally right that the pole shifting was also available, and in that way you had two times you were harvesting the maximum energy out of the weight of the wind according to the blades. Yeah,
And when
that's true.
you go with this power electronic conversion completely through, also I do not mean the 30% generator, 30% power, what you need for generating the field in the this upper picture here. The upper picture, it means it would require a machine with with a slip ring for
It's great.
pumpen. Okay.
Yeah.
How do you see this?
Well, wind turbines, but that's one of the disadvantages. But I have, so let's say if we go 10 years back, the upper one was more than 60% of the whole installed fleet in the world. Because it is to a certain degree acceptable because you anyway do maintenance programs on the turbines. So even though you have slip rings which demands a certain maintenance, because also other part gearboxes, others have a service interval of 1-2 years, then you can accept, let's say, also such part of the service program.
But they are also in both pictures. Let's say you can, the wings, you can put them with this pitch out of the wind. This is almost necessary in both.
Yeah, so this is to control, let's say, the power also. But
and if in emergency too much wind, you turn them out. So you
totally
make.
Totally right. Yes.
Okay, interesting. When I was before I become a professor, I made the power supply for this pitch generator.
Yeah. Right.
It was a challenge because also they told me they are also turning around this kind of power supplies, and we had big issues with vibration and so on. The power supply itself was not an issue, but the vibration,
yes.
the mechanical,
Yes.
Okay. Are there some other questions?
Okay, but then maybe we should move to you, Michael. What do you say what does the chairman say? I think the time is 48, so depending on.
Thank you, Professor, for the enlightening session. Now the session is open for queries. I request the participants to post their queries in chat box, or you can ask directly.
Yeah. Okay. Okay, so there was a question here, hybrid energy integration. How can offshore energy hubs be optimized to seamlessly integrate multiple renewable energy sources such as wind, solar, tidal energy, along with energy storage system to create resilient and self-sustaining energy ecosystem? Yeah, that's a big question to make, for example, such kind of energy hub, if we can say so. But I would say the key to do it is for sure the power electronics technology, because we have to put everything into DC or AC. And in terms of optimization, things will depend fully on the conditions where we place it. If it is a good wind area, then I would say there are a lot of focus on the wind. If there are good sun, then and not so good wind, then it has to be scaled differently. So this will depend a lot on the local environment. Thanks for the question.
Thank you, Professor. Any other queries?
Okay, so how can autonomous maintenance strategies use robotics, drones, and remote monitoring system be developed to ensure the continuous operation and on-keep of offshore energy hubs in harsh marine environments, minimizing downtime of operational costs? Well, I think we can all imagine that if the wind is extremely high, it's difficult to use drones and so on. But there is no doubt that a part of the maintenance programs and also the service and inspection programs today in the wind industry are based on drones. There's no doubt. And even automatic inspection, for example, the blades, how do they look? It's possible to use drones with good cameras and so on. This is already a part of it. And I also think now we are going to hear about PV. We also hear about drones, which are inspecting the plant. It's not working or not true. I don't know, but you are
I have no
expert.
experience.
No, you have no experience. But I have had people who visit me and they tell me.
I know also people who fly around over the solar plant and having this thermal cameras,
exactly.
and you can see which string works not. Okay, I do the same. Okay, why I do? Okay, my colleague has a solar plant, and I watch through the camera and see that half of it will not work.
Okay.
But it can be done by drones.
Yes.
It can be also. There is a company here. They clean it with drones, but I never seen it.
Okay. Now, but there's no doubt when we go offshore, 100 kilometers away, and we cannot afford to have cranes up, let's say, all the time. Drone is important, as well as they are applied for bridges and so on. This gives absolutely new opportunities, and also say for research, there are a lot of new opportunities.
Sir, I have another question regarding distribution side control there in Denmark. I would like to know whether micro PMUs, that synchro phases, has been installed there in distribution side or not. I think it is different. I think it's a control area. See, we'll be having different regional wind power, solar power, etc. And then distribution, grid control, etc. We need some synchro phases, micro phaser measurement unit.
Yeah. Okay.
Implemented there or not?
as our country is small, your country is very big. So in our system, we have PMUs, as a phasor measurement units, located at the transmission level, but not very low at the distribution level. Because we have a very strong grid. So the control is mostly based on, let's say, at the transmission level, and there are no, let's say, control at the very low distribution level. But I would assume that I think that is a wise thing to do in case that let's say the grid is more volatile, and you have to be able to control also more at the local level the power flow and the frequency.
Okay, sir. I understood. Thank you, sir. Thank you so much. Any other queries from participants?
Good afternoon, sir.
Good afternoon.
So I would like to ask a doubt. How can smart technologies be effectively integrated into existing power grids and renewable energy systems?
And by smart, do you mean, let's say, where you take decisions based on what has been happening in the grid? Or because I would say, when you look, for example, at the control structure of a wind turbine, like I showed for you in the presentation, I would say there are parts of this control structure which I would say is to a certain degree smart. Some would maybe say it's dummy, but it is smart because it's able to adapt and handle situations on the grid where if you did not do anything, then there is a high risk of let's say collapse in the system, or there is a high risk of damage of the equipment. Having been said that, I see more and more activities where, let's say, the control of the distribution system becomes more and more dependent on data which have been measured over time, and based on this, new decisions are taken in terms of the operation. So I see a lot of opportunities in using, let's say, what you call smart systems in it. And another one is forecast, right? Forecast looking 1 hour, 24 hours ahead. For me, this is also some kind of smart and also data-based. And so I think it's evolving, let's say, in a steady, good progress.
Thank you, sir.
Any more queries left?
Delegates?
Oh.
Any more queries?
Nothing is
there.
there.
Anything posted there? No.
So may I invite Ms. Deepa K, Assistant Professor, Electrical and Electronics Department, to deliver the vote of thanks. Ma'am, please.
Thank you, sir. Thank you so much. It was a very enlightening session for us, for all the delegates and all our BTech students. And I also got very, very, very relevant information from that. I'm doing research in smart grid and synchro phases. And it was a very, very relevant information I got from this session. And Energy Island was a very new idea for us. I think in India also we can implement such things, I think. And thank you, sir. Thank you for your patience, and thank you for your answering all our doubts. Thank you, sir. And
You're welcome.
On behalf of FISAT and on behalf of coordinators of this international conference, I would record my heartfelt thanks to sir.
Thank you very much. An honor.
Okay, sir.
Thank you, sir. move on to our next keynote lecture. It's our pleasure to welcome an eminent person to enhance this session. We are extremely privileged to have Professor Dr. Michael Patt, Head of Power Electronics, Kempten University of Applied Sciences, Germany, to deliver keynote lecture on the topic. I am honored to welcome Professor Dr. Freddie Blackjob to introduce the distinguished speaker for this session. Over to you, sir.
Thank you very much. And Michael Patt got a PhD degree from University of Federal Armed Forces in Hamburg, Helmut Schmidt University in 2002. After that, he has been in industry in the field of power electronics for PV inverters, chargers, drive inverters, and welding inverters, all topics illustrating the importance of power electronics. And then he has been a professor since 2012 at Kempten University of Applied Sciences and also director of the Institute of Power Electronics. And he is the spokesperson for this university for the research area of energy. And he lectures also at Technical University of Munich in renewable energies. Work with power electronics and application, of course, in PV, e-mobility, wireless power transfer, chargers, wide bandgap semiconductors, and EMI. So I think the topic here is about characteristics of transformerless photovoltaic inverters, and I think it aligns very well. Now I talked about the wind, and the other one, which is extremely important, is the photovoltaic, and the power electronics is, of course, also very important there. So, Michael, please.
Yeah. It kicked me out. Can you see me? Can you see my screen?
Yeah. Can you make full screen?
Full screen.
It's not full screen,
It's
sir.
not
We can
full
see the
screen.
വേണ്ട ചെയ്യണം.
Just mute.
Yeah. Yeah. I think
Maybe better.
that's good.
Okay, sorry for this technical issue. Yeah, okay. Google was new for me. Okay. Thank you for the introduction. We are in the University of Applied Science in Kempten, which is in the south of Germany. But our institute is not located in Kempten. The politicians wanted that. It is maybe 1 hour away because the politicians think we are then closer to the industry. We are located in this building here, and you cannot see it. On top of the roof, we have installed maybe 20 kilowatt of solar power. I want to put there also a small wind turbine, but we are talking here just about 1 kilowatt or something like this, just for the students. We have here, I want to mention it, we have here in Kempten's a program for, we have an English master, so also for let's say foreign students, they can come here and study. Of course, something else. Power electronic is the most important, but there are also some other topics in the study. And we have also some PhD program here. And I will talk about characteristics of transformerless photovoltaic inverters. It is a paper related to the hardware of the photovoltaic inverters. And I want to show you how it works and what is problem. we will talk first about grid coupling of a photovoltaic inverter. I almost talk they should be capable of reactive load. There's some difference. First inverters, or depending on the circuit, they are not capable of reactive load, but this comes more and more important. And I think also when you don't have capability of reactive load, maybe small inverters are available, but they are not very often. Okay, then I will talk, I finished the AC side, I will talk about the DC side. I will show you what means when we talk about a three-phase inverter, and then I want to compare three-phase with three single-phase inverters. A lot of people asking me this, and afterwards I come to some conclusion. Okay, what is a PV inverter? We see here a single-phase PV inverter. We see here on the very left side, we see here a series connection of PV modules. Since the PV modules are acting like a current source, and when we have here a voltage source inverter, we have to make from a current source a voltage source, and this is how we do this. We take here a capacitor as the input. And then we got 4 switches made by semiconductors, and these 4 switches are generating alternatively a PWM pattern. For example, switch 1 and switch 4, they act together. So when you turn switch 1 and switch 4, you will have here at the blue arrow, you will get the plus of the DC. When you turn on switch 3 and switch 2, you will get here a minus. And when you do so, you can generate a PWM frequency. Since this inverter acts like a buck converter, we have to, at the DC side, we have to be higher than the AC, than peak value of the AC side. In Europe, okay, 230 volt multiplied by root of 2, let's say plus 20%, because the PV can also lift up the grid. So we say minimum voltage maybe here is 390. When you want to connect this to a grid, when you have 2 voltage sources, you need something between, and this is done by some inductor. It's a relative costly part in a PV inverter. So on the left side, we have our PWM. On the right side, we have the sinus of our grid. And when your controller works all right, you will have here a sinusoidal current with a ripple on it. And it flows into the grid. What do we want to have first? We want to have in our grid real power. So that means this current here and this voltage should be somehow in phase, otherwise we cannot have real current. But we need there an X capacitor also in my inverter, because we cannot say that the grid is an ideal voltage source. We will have here, in the grid is an inductive reactance. Normally, we can neglect here the ohmic load, and then it results into this fundamental equivalent circuit diagram. I mean with fundamental, that here I talk only about the 50 hertz current. So when the sun is shining with a lot of radiation, and we want to have here in phase with my grid voltage, my grid current, then we see that we will also have a current flowing through my X capacitor, and this is a current what comes out of my inverter, because this is sum here, the sum this current plus this current gives my inductor current. But what happens when the sun the radiation goes lower, because of we are reaching the evening or what, and my inverter just works with 20% of the power. My X capacitor, of course, it stays, and since it is connected to the constant voltage of the grid, my X capacitor current will be the same. My grid current will be lower, and then you see, okay, I'm becoming here more and more reactive. So it means my inverter needs to have the reactive power capability. There are circuits available without reactive power. There are circuits available with reactive power capability, but inverter needs it. One example is this kind of inverter for switches, and these 4 switches are generating a bipolar PWM pulsing. It is called, you see, it is between plus and minus DC. Here is related to 1, and it means I have this diagonal switches or this diagonal switches if you have plus or minus. The voltage drop at our inductors, later on we will see why we have here 2, because, okay, series connection, we can say there is only 1 inductor necessary. But the main thing what I want to say is the inductor voltage is the difference between the sinus in the grid and my PWM, which results into this voltage. Now, you know, when you want to save costs, you can have the idea to go from bipolar PWM pulsing to unipolar PWM pulsing. This can be it can be achieved by the inverter. Beside plus and minus, you can also fill in here some zero sequence, and the zero sequence can be done, for example, if the both lower switches are on or if the both high side switches are on. So, and then the output voltage of my inverter is 0. This results into, an inductor voltage, which is better for the inductor. We have here only 50% of the voltage time integral, and this results then in a half size of the inductor value, what you have formally when you do bipolar switching. I mentioned before the inductor is a very costly part in your inverter, and this is very, it's a big price driver. Okay, but let's go a little bit deeper into the inverter. I show you here again the equivalent circuit diagram. One pole of the grid is connected to the protection earth. This is the symbol for it, and it consists of 4 switches and 2 inductors. Our PV plant is very big. You know, when you have, for example, 5 kilowatt on your roof or somewhere assembled, it will be, I think it is 30 square meters, is a big area. And this frame where it is assembled, it has to be also connected to the PE. And this results in 2 earth capacitance. The capacitance are here, say, between the modules and PE, but you can use some trick to sum it up into a capacitor which is from plus to the ground and minus to the ground, and these are not neglectable. When you have a 5 kilowatt plant, you can say that the size is 100 nanofarad when it not rains. When it rains, you know, water has, or maybe you know, I know water has epsilon R at about 100, you will increase the capacitors here. So they are not neglectable. So what happens here? Okay, before we start, you will see that my PV voltage is divided by the capacitors C1 and C2. So on both capacitors, there is half of the PV voltage. And now we turn the diagonal switches, switch 1 and switch 4 together on in order to get plus. So when we do so, we see that my capacitor 1 is now parallel connected to the inductor L1, and my capacitor 2 is now in parallel to the, this is to the inductor L2. This equivalent circuit diagram is not completely right. When we start our PWM and we say my PWM is much more faster than the fundamental of the grid, then it doesn't matter if it is here or if it is here. So these two inductors must have the same size. So L1 equals L2, C1 equals C2, and we get here a voltage divider. Half voltage will be here and half voltage will be here. So there is not a too high DVDT on my capacitors, and the voltage results into, PV voltage half plus the AC voltage, PV plus AC voltage over 2. Okay, and now when we turn to the negative voltage, we see something again. The capacitor, the upper capacitor, is now in parallel to the inductor L2, and the low side capacitor from -2 ground is parallel to L1. So I changed these two capacitors, and this is what I'm doing in each PWM pulse when I'm changing it. Voltage is same, again, PV voltage plus AC voltage over 2. Okay, now when we want, now we have understand our bipolar pulsing, and when I want to switch now to the 0 in order to make unipolar pulsing, then happens here a strange thing. The equivalent circuit diagram results into this, what you see here, and the voltage results now into, the voltage of capacitor C2 results now into the AC voltage over 2. That means from here to here, you provide to this, or the circuit provides to this capacitor, let's say an infinite DVDT, and this cannot work. So there's a problem when you want to switch into the freewheeling state of the H4 bridge. So what to do? There are several ideas. I forgot. Okay, when we do everything all right here, we see here the voltage curve of the parasitic earth capacitance in bipolar pulsing, inverter output between plus and minus, and upper capacitor, lower capacitor voltage. Between we have the grid. The distance here is the PV voltage, and the sinus here on top is half of the grid voltage. When we try to do unipolar pulsing, we see here a jumping voltage on a capacitor, and this cannot work because with this high DVDT we will have a lot of current, and we have here a safety problem. I talked with colleague Blaberg about drones who clean the PV modules. Okay, you can also clean the PV module by yourself with your hand and rope and something like this. But what is your hand? Your hand acts like a capacitor, And okay, when you are standing on your ground, the human body is a capacitor. And then here, when you touch the module, there can flow current through your hand capacitance. And this is a safety problem. So we cannot do this. We need other circuits. One circuit here is, a circuit which is called HERIX. The abbreviation is called highly efficient and reliable inverter concept. And the trick behind the circuit is, the free running path, what you normally send to the low side or to the high side is now, it is possible that this current can flow through this bidirectional switching element. And this circuit becomes established. You can achieve also with this very high efficiencies up to 99%. It was invented by Heribert Schmidt from the Fraunhofer Institute in Freiburg. Yesterday I have read something in the newspaper here that there are 80% of this of all single-phase inverters worldwide are made by this circuit, but 80%, not all of them are allowed. They have a lot of patent problems here. So this concept here offers us a 3-level output voltage. The current and voltage waveforms are like this. We have here output voltage and current in switch 1 and switch 3, or in the bidirectional switch you can see here in this picture. It has the next advantage. There is also no commutation from a diode when you use here pure active power. It is, when you are deep in the power electronics, you will know that the commutation away from the diode can be a problem if you have a slow diode. So this is a way how to couple the inverter to the grid with unique polar clocking. Let's talk now about the DC coupling. At the very left, the first element what comes is a DC link capacitor. So we have to make out of the current source from the module a voltage source, because we have here PV inverter. We make the following assumption. We say the instantaneous input power equals the instantaneous output power. And with this, let's say we can calculate the DC link capacitor current, because this is the next costly element in my PV inverter. So when we have a deeper look in it, with bipolar pulsing, we will have here a DC link capacitor current, which is like this. Around here, you will see this is load current. And when you calculate the RMS value of this, maybe the RMS value formula, you have to square it. And you see that this here is, let's say, it depends not on the modulation index. The full load current goes into my DC link capacitor. And when you use unipolar pulsing, we see the capacitor current here in the black curve, and this is now depending on A. This is normalized to the peak value of the AC current. So you can here, let's say, if you say this is 100%, we can say this here is 50%. So far, so good. in these two waveforms here, there is all the current in the DC link capacitor. When you would do a Fourier series from it, you will have a 100 Hertz part and you will have a PWM part. The PWM part in higher frequencies are easier to filter, but the 100 Hertz part, the part with double frequency, plays here a big role. Okay, why do we have here 100 Hertz? Because, okay, when we have here at the output, at the grid, let's say, when we have 50 Hertz in the voltage and we have 50 Hertz in the current, both are in phase, then we will get sinus multiplied by sinus, and this gives sinus to the power of 2, and this is 100 Hertz. And this 100 Hertz current flows through this capacitor. What makes it? It makes a voltage ripple. This voltage ripple interacts with the solar generator curve. So I have put here a solar generator curve at one certain radiation, at one temperature, doesn't matter. And here is my DC voltage with a ripple generated by my 100 Hertz current. And the current, what comes out of my module is, when you make somehow like a mirror here in this curve, you get this current here. This current here, okay, it looks sinusoidal, but it is not really sinusoidal because this curve here is in this piece here, in this piece of the curve is not linear. In this point, we have the MPP point. And when we multiply this both curves in order to get the instantaneous power, we will get a curve which looks a little bit strange like this. So we have here a curve with an amplitude of 10 volt RMS in the voltage amplitude. And when we average this curve, it should be, as an example, I used here a 5 kilowatt inverter. We will have here 4.65 kilowatt, what I extract out of the module. In the other picture, we just doubles the size of the DC link capacitor, so we will get half of the RMS voltage like before. And yeah, of course, more capacitor, the voltage is more smooth, and then the power, instantaneous power, is more smooth. But the interesting thing here is when you average the power, you get, 30 watt more. Okay, 30 watt more sounds not very much, but when you think that the PV inverter works, let's say, the whole year, and when you then sum up your 30 watt, and it should last 20 years, then 30 watt will give a lot of kilowatt hours. And, kilowatt hours means money. And from this money, I would be able to buy somehow a couple of more capacitors. Honestly, the manufacturer do this not, because for the manufacturer, it is too expensive. They want to save costs. So it really looks somehow like this when you buy an inverter, let's say, in the market. Okay. This 100 Hertz problem occurs only in a single phase application. So what about three-phase applications? A three-phase inverter can be like this. There is also the neutral point clamped circuit available in, or there was a neutral point clamped circuit available. Same that was in the slide from colleague Blaberg, but okay, it is not very often anymore. Let's say 10 years ago it was available. Okay, a three-phase inverter looks like this. Here's the same problem with parasitic capacitors from the modules. So they are here, they are not drawn in the circuit. But when you connect your zero wire or your PE to the center tap of the DC link capacitors, then it works, because when the voltage here jumps, not the voltage, or it is fixed with these two big capacitors connected to ground. But the problem what we have here is, since my PV inverter acts like a buck converter, my DC voltage should be more than the voltage now it is between in here. So, but this voltage is 230 by root of 2 by root of 3, because of the three phase, plus again the 20%. We are at 670 volt. This 670 volt, below it will not work. My maximum voltage, what I can have here at the left side, is theoretically, let's say, okay, it is unlimited, but there are some rules what we have to follow. There's a rule VDE 0100 is in the Germany rule. It offers a maximum system voltage up to 1500 volt DC system voltage. But honestly, all the most equipment, cables, also modules, connectors, is only isolated up to 1000 volt. You know, when you go higher than 1000 volt, it gets expensive. So, but what is the problem here? Let's take a look at the PV module curves. They are very temperature dependent. In this picture, we have same radiation, but different temperatures. The output voltage of my module or my MPP voltage depends very high on the temperature. We have here in Germany, especially in the south of Germany, we have to calculate with minus 25 degrees. And, you know, this is open circuit voltage. And when my module works, of course, the temperature is increasing. So I'm walking on this points, let's say, to the left. The reason is my PV module is a diode. So, and let's make a roughly calculation. When this is 100%, the maximum open circuit voltage, the minimum MPP voltage at high temperature means a lot of current flows and the sun is shining on the module. We get here 60% delta. So back to the slide with my 670 volt and my 60% variation, temperature-based variation, it will not work over the year. So half of time your three-phase PV inverter will be off. What to do? We take here some boost inverter for PV voltage adjustment. This is a way how to overcome this problem. We take here a simple boost, but it will reduce the efficiency. So pay attention. So the question is now, should we use, what is better, let's say, is one three-phase inverter with a booster better than in comparison to three single-phase inverters, what we separate on the phase. So, like this picture here, one three-phase inverter or three single-phase inverter. As an example, I took here 15 kilowatt because I had 5 kilowatt in the lab. My last booster, what I made for a PV inverter, had an efficiency of 99%. So, and when we calculate now a 15 kilowatt inverter, 1%, efficiency means I have here 150 watt loss. Here you see exemplary a picture of a single phase inverter with my 100 hertz ripple. It is what to say, maybe 25 or 20% of the whole PCBs. We have here DC link capacitors. A 5 kilowatt requires 3000 microfarad. When you calculate with some ESR from 200 milliohm and with our 100 hertz current, we get 30 hertz, 30, not hertz, 30 watt loss. So my capacitors have a loss and my three-phase booster efficiency has a loss. And yeah, okay, outcome is 120 watt more loss in the three-phase inverter. The overall efficiency is here reduced by 1%. So the question is now, is the three single-phase inverters are much more expensive than one three-phase inverter. You have three housings, you have a bigger capacitor, and so on. All the small electronic is the same. It is a costly solution, but should we go with with the three single-phase inverters or with one three-phase inverter? When you calculate 1% loss, and it depends how much money you get for your 1% energy per year, per 20 years, it should work for 20 years. This, let's say, you can answer by yourself. So, and this was the end of my presentation, and thank you for the attention, and I'm waiting now for questions.
Okay, thank you very much. Now the presentation is open for discussion. So maybe we can do it the same way like before. I give one or two questions, and then you control it from your place. The questions from your side. I have a very interesting and very important to know about, let's say, the PV and its inverters. In your calculations in respect to single phase versus three phase, and you say 20 years, have you assumed 20 years of lifetime of the capacitors?
Yes.
Because typically the load of the capacitors in the three-phase system will be a little bit different, right? Because you can provide constant power out to the...
Yes, this is a big advantage in the three-phase, and this makes the three-phase inverters also, it makes it cheaper, let's say.
Okay.
It makes it cheaper. Okay, let's say, I am not the youngest boy anymore, and I do this for 20 years. So I know I can see my inverters, what we produced 20 years ago.
Yeah.
They are still working. And okay, when you are doing the inverters, I was responsible for the lifetime calculation for the capacitors.
Yeah.
Okay, not all the inverters work anymore, but the problem is not the DC link capacitor.
Okay.
So the DC link capacitor was good. So this worked. When you start with this thing, you cannot look into the future, but now I know that the capacitors, it was working.
Okay, so maybe you can elaborate on where do you see the failures of what you did design for 20 years ago?
Yes. Should we really talk about this? Okay.
No, but it's interesting. I mean, of course, we know more today, so it can be different.
Yes, it is an interesting thing. You know, how to say, we developed inverters. What happens when you have a failure in the grid? You have to turn off the relays.
Yeah.
Okay? You turn off the relays, the inverter is disconnected, but your IGBTs, your bridge, is still running. Okay, so let's say you have on the left side of the relays, there is a big rectangular voltage with the height of the DC link voltage.
Yeah.
Okay, and there is the bias power supply connected.
Okay.
You understand what happens?
Yeah.
When it goes off, my bias supply is for a small time supplied by, let's say, 800 volt. Normally it is supplied by 230 volt by root of 2. But this is a mistake made by me, made by us, let's say, by the developers. This is a problem.
Okay.
But what we find out, what is problem? We have a lot of IGBT bridges.
Yeah.
You know, we are also doing this kind of research. We have IGBT bridges, power supplies. And okay, what we have also is some things which is not related to the power electronics. We have some water problems,
Yes.
let's say.
Humidity. Yeah.
There is on a display, there is somehow a film. You can press a couple of buttons, and there it is glued somehow, and there comes the water inside.
Okay.
This is okay.
Good to know. It's not all about
and
capacitors.
rust. They are rusting.
Okay.
Yeah.
Okay. Yeah.
Where the stray field of the inductors, they make somehow heat in the shield, and there the color is then not anymore good. So
okay, super interesting. Now I will leave you to raise some questions from your side also.
Any queries from participant side? So do you feel grid-connected inverter needs an galvanic isolation, which plays a role of output filter as well as galvanic isolation? Secondly,
so galvanic insulation is normally not necessary. You can have a galvanic insulation, but it is costly. This galvanic insulation is, you can, when you put there some transformer with a winding ratio 1:2 or something like this, you can make there some adjustments with. But normally, 20 years ago, there was somehow advertising for galvanic insulation, but it helps not in safety, it helps not in reliability, and it is only costly. So it is normally not necessary.
So one more question. Electrolyte and film, which type of capacitor you suggest as a DC link capacitor?
You talk about, your audio is a little bit bad. You talk about the DC link capacitors?
Electrolyte and film, which type of capacitor you suggest as a DC link capacitor? Yes, sir. DC link capacitor.
Yeah, of course, DC link capacitor. We use electrolyte, let's say normal electrolyte, nothing like lithium, ion, polymer, whatever electrolyte. This is too expensive. We use normal electrolyte capacitors, and we make a lifetime calculation, and fortunately this works. For three-phase inverters, you can use film capacitors. This is possible. This is also possible, yes. But in single phase, there is in single phase there is electrolyte. You have written it also. Do you feel grid connected inverter needs galvanic insulation in terms of transformer? No, they don't need, which plays a role. The problem, the thing with the transformer. Let's say 20 years ago or 25 years ago, when it all starts with this PV, there were transformerless and transformer inverters with transformer available. So, and the people believed that when they go into the bed and the big solar plant is on the roof, is over them. And when there is a transformer, they can sleep better because there are no, I don't know, voodoo radiations from this 50 hertz. So it was it was just for advertising having some transformer. So in these days there is no. When there's one thing, when you have small inverters, like for balcony, which has a very small power, let's say 600 watt, 500 watt, then a transformer makes sense because there's one trick. The small inverters have low voltage. For adjusting it, you need the transformer. This helps here, and it helps in a second way. You don't need a RCD. So in a small inverter, it is better having a transformer for adjustment and no RCD, a residual current breaker. This is some trick. Okay.
Any other questions?
Good afternoon, sir. Sir, what new MPPT algorithms improve solar energy harvesting in DC coupled systems?
What MPP do we use? We make let me think. We make a DP over the V measuring. You know, when you have this MPP curve, and when you are left or right, you make a DP over dV measuring, and when it is when this derivation is 0, you know that you are on the top. And we do this normally after we have the next value of real power. Yeah, you know, real power is normally after not after one period, we can do this after half period of the grid. We have a new power value, and then we can adjust. And we adjust it with, yeah, the steps are 2 to the power of 12, also digital steps divided by my MPP range made by my controller. What is the answer? So, some more questions?
Any queries left? So can you read in the chat box?
What advantage can be made in multi-terminal grid interconnection to enable the efficient coupling of multiple inverters to a common grid and facilitating the integration of distributed? Yeah. You know, when you connect multiple inverter into a common grid interface, let's say it's a fine thing, it works. The only thing, you need a communication between the inverters. The communication between the inverters is made, or we do it with RS485, or we do it with, let's say, kind of internet, and until now we made measuring in a microgrid. You know, we have here around a couple of kilometers away from here, I have a microgrid. I can supply a couple of streets from a village with as an island grid, and of course there is also some things like let's say the dishwasher is shifted into the time when the sun shines. So this it is possible. The only thing you need big software and communication between all the measuring places, and you need some algorithm. But the communication there is, let's say, most important. Okay.
Any queries? I think
Can you
nothing.
repeat?
I think nothing left, so we can move on to next session, sir. No queries left. Okay, so thank you, Professor. May I invite Mr. Agar Sabu, Student Representative, Electrical and Electronics Department, to deliver the vote of thanks.
Thank you, Rinku ma'am. On behalf of Department of Electrical and Electronics Engineering, I extend my heartfelt gratitude to Professor Michel Sir for enlightening us with an insightful discourse on smart technologies for power and renewable energy. Your expertise and passion have left an inedible remark on our understanding of this vital subject. Your explanation on grid coupling of inverters shed light on intrinsic interplay between renewable energy sources and power grid, paving the way for a more sustainable and efficient energy ecosystem. Furthermore, your explanation on the freewheeling state of age of bridge illuminated a crucial aspect of power electronics, showcasing the importance of mitigating switching losses for optimal system performance. Additionally, your discourse on the characteristics of transformerless PV inverters provided invaluable insights into innovative solutions driving enhancements in photovoltaic technology, emphasizing safety and efficiency in solar energy generations. You also mentioned about the safety problems related to solar panels also. Lastly, your comprehensive overview of three-phase inverters underscored their pivotal role in facilitating the integration of renewable energy into the grid, ensuring stability and reliability in power distribution. Your expertise has enriched our knowledge and also inspired us to delve deeper into the realm of smart technologies for sustainable energy. We are immensely grateful for your time, dedication, and invaluable contribution to our gathering. Once again, I thank Professor Michel Sir for enlightening session. We look forward to your more collaborations inside the future. Thank you, sir.
Thank you, Professor Blackjack and Pat, for being with us. So with this, we wind up online keynote lecture sessions today. We shall break for lunch now. Parallel paper presentation sessions will be held as per schedule in conference room DB 407 and IEDC room. Thank you all.